Hello and welcome to the fourth session of my lecture about bending members. In this session, we're talking about the moment resistance of laterally unsupported members. It is on clause 13.6 of S16. So far, it has been assumed that the strength of the beam is determined by the capacity of its cross-section. And now, we have to consider that it is dependent on the local buckling of the plate elements as well. Okay, lateral torsional buckling. If a beam is not laterally supported, then the strength of that may be governed by lateral torsional buckling. It is twisting and bending about the weak axis, and we're going to talk about this more. This would cause failure at applied moment significantly less than full cross-sectional strength. So probably definitely our moment will be lower than plastic moment. And it will happen for the laterally unbraced members, which L is bigger than unbraced lengths. Lateral buckling capacity depends on the unbraced lengths and a variety of cross-section properties. A lateral buckling of a beam is analogous to first-shore buckling in a column, as both represent ideal situation. As columns are not perfectly straight, beams contain perfection, so lateral deflection will be there even before loading. Like columns, unbraced beams can be classified into three categories: stocky, intermediate, and slender members, based on their failure mode and the slenderness ratio. When a beam is subjected to bending moment, the cross-section moves vertically from its initial position. As you can see in this picture. At the same stage of loading, the cross-section may twist and bend about its weak axis. Therefore, lateral torsional buckling has occurred. So, both bending and torsional and twist about its weak axis. It can happen at any stage of the loading after the member reaches plastic moment for class 1 and 2, between My and MP for class 3, and lower than yielding moment for class 4. A stocky beam is defined as a beam that is able to reach its local buckling capacity before lateral buckling. So before it reaches MP for class 1 and 2, and Y for class 0 or lower, and Y for class 4, the local buckling will happen in stocky members. But an intermediate member, which has an inelastic lateral buckling, has a bending moment at the instance before lateral buckling that is sufficient to cause portion of the member to yield. So that moment will cause a portion of the member to yield, so therefore it will be reduce the resistance of the member to both lateral and twisting motions. What is a slender member? A slender beam buckles laterally before reaching to the yielding moment. So it buckles elastically. Okay, the resistance to lateral buckling depends on EI of the weak axis, and twisting will be resisted by Saint Venant resistance, which is a function of Gj. G is shear modulus and J is Saint Venant torsional constant, and wrapping resistance Cw, where Cw is the wrapping constant. For a beam subjected to end moments producing a constant bending moment distribution and having simply supported boundary condition, the moment at which the lateral torsional buckling will occur is given by this formula. So this is for a simply supported beam subjected to end moments this is free body diagram, this is bending moment diagram, so this formula is for this situation. Therefore, this formula is conservative for most cases, because since bending distribution is not likely to be uniform at all cases. Since not all the members will be subjected to uniform moment throughout the length of the beam between the points of lateral support, a modified omega 2 has been introduced. So we add a modified factor omega 2 to modify this formula for the other conditions, because it is not likely that we have the constant moment during the length of the beam. Omega 2 is dependent on the loading condition of lateral support, and moment gradients that exist between the point of the lateral support and is given by this formula. This formula is introduced for nonlinear bending moments, such as this one. For example, consider this is the laterally unsupported length of a beam. If we divide this laterally unsupported length of the beam to 4 segments, and each of them is LU over 4, by using this formula, we can calculate the omega 2, which Mmax is the maximum factored bending moment, Ma is the factored bending moment at 1/4 point, so this is Ma, Mb is in the middle, Mb, Mc is in this point. Be careful that this formula is working for non-linear bending moment diagram. The other formula for omega 2 is this formula you can see here. And be careful that the upper bound for omega 2 is 2.5. Kappa in this formula is the ratio of the smaller bending moment to the larger bending moment at the opposite end of the unbraced lens. And it is positive for double curvature and negative for single curvature. When the bending moment at any point within the unbraced lens is larger than the end moment, omega 2 is 1. So for example, if you have a simply supported beam with a point load, omega 2 is going to be 1, because you have a moment and the midspan is larger than the end moments, which are 0. When there is no effective lateral support for the compression flange at one of the ends of the unsupported lens, omega 2 is 1. So when you do have a condition that you don't have a lateral support at your boundary conditions, at your ends, therefore you have to consider omega 2 as 1. If you look at this table, you can find some examples. For example, look at this L1 here. We do have M1 and 0. Therefore, kappa is going to be 0 because ratio of the smallest to the biggest will be 0. Then omega 2 will be 1.75 for L1, which is the same for this side. And L2 will be 1. Why L2 is 1? Because we have a beam embrace lens that has MF1, factored moment 1 for here, and factored moment for here. At this point, these factor moments are equal to each other. So if they're equal, it means that the moment is constant in this embraced lens. Therefore, omega will be 1. Now, if these two moments, factor moments, were not equal, as you can see here, kappa is equal to minus the smaller one over the bigger one. And because this is a single curvature, it should be negative for L2. Now, consider this embraced lens. Because we do have a factored moment that is bigger from one of the moments at the supports. This one is 0, so definitely this factored moment will be bigger than this one. Therefore, omega 2 for L2 will be 1. Thank you for listening to session 1 of this lecture. Please comment or email if you have any question.